So welcome to our first morning session today. So we have two talks. The first one is by Sarang Gopalakrishna. It's going to be telling us about persistence of quantum coherence in high temperature dynamics.
Thanks very much, Marcos. I was very much looking forward to being there in person, but yeah, my passport didn't survive the trip to the consulate, and so here I am speaking remotely. Okay, so I want to tell you today about something rather surprising that my postdoc, Ewan McCulloch, discovered earlier this year about quantum dynamics at high temperatures, and it's in this paper. So as context for this project, a big question nowadays is how quantum is many-body physics anyway? Do you really need a quantum computer to simulate any of it? If you don't, you're happy because this guy is spending a lot less money than this guy, and that's nice in this economy. If you wanted to study many-body physics to arbitrary accuracy for arbitrary observables, then you probably do need to simulate it quantum mechanically. But what if you only care about getting some subset of quantities right to some finite precision? The same question arises even classically, if you have a system with many particles and they're interacting in some complicated way, predicting even, a gas consisting of a bunch of particles bouncing around inside a box, predicting individual trajectories of the system is hopeless. But of course, that's not what you're trying to do in practice. What you're trying to do in practice, if you want to, for example, study water flowing in a pipe, is you want to develop some coarse-grained description and predict some coarse-grained quantities, again, to some finite precision. And if you want to do that, then we know, especially in this workshop, we know how to proceed. And the way you proceed is by doing hydrodynamics. And the way you do hydrodynamics, you say, locally, any very complicated dynamics is essentially random. And so because of chaos, and so the system rapidly goes to the maximum entropy state, the most random state, subject to whatever conservation laws it's subject to. And if you play this game locally, if you play this game globally, you get thermalization of the full system. If you play it locally, you get hydro, because you say locally a system is in some thermal state described by local values of conserved variables. And then, of course, you can write down equations for how those local conserved densities, those local temperatures and chemical potentials evolve according to gradient expansion or something else. Okay, so in one dimension, not very much happens here. All that you get on the lattice is diffusion. And very importantly, diffusion is a purely classical theory, regardless of whether you started with a classical or a quantum system. And you could ask where the classicality came from. And so sort of very loose picture of where the classicality came from is you think about one quantum particle moving inside a medium that's at finite temperature and consists of all the other particles in the system. All the other particles are drawn kind of randomly from the thermal distribution. So particle takes some trajectory, and depending on the precise trajectory it takes and the path integral, it picks up a random phase, and the random phase depends on the locations of all the other particles. So now if you think about the density matrix of the time-evolved guy, what you find is that the sum over trajectories is going to dephase unless the bra and the ket took very similar paths that collided with the same other particles. And so for the trajectory to survive the dephasing, it needs to be kind of classical in the sense the bra and the ket need to be close together and just replace the trajectory with its center of mass location. And that's sort of the precise sense in which it's classical. Okay, so the reason I'm sort of reminding you of this picture is that it's got an important implication, which is that interactions with other particles act more or less like noise. The system acts more or less like its own high-temperature heat bath. And so you might think intuitively that adding extra noise, so coupling the system to an external heat bath at the same temperature, is not going to do very much to the behavior of your system. On the other hand, it might make it easier to simulate, and the computer scientists have some results saying that, in fact, noisy evolution is simple to simulate. And so you might say, okay, this approach is going to allow you to maybe extract useful information efficiently about the dynamics of complicated quantum systems by essentially treating them as classical, by coupling them to external heat baths. And so one thing you might try to do if you wanted to use this idea and make it a concrete like paradigm for quantum simulation is you could say, okay, what I'm going to do is I'm going to couple my system to bath, and then roughly speaking, in the presence of a coupling to a bath, my spectral functions are going to look like featureless blobs. When I take and that's going to be because I broaden them with noise. When I take the broadening to zero, and in the thermodynamic limit, there's still blobs, and therefore I can just sort of take the limit. The limit is smooth, and so I can just imagine taking the limit in the obvious way. So that's the idea of zero noise extrapolation. Another way to say it is in real time, my correlation functions in time decay rapidly. My noise just gives me an extra decay factor that's tiny, and so it's not going to do very much to put in the noise as long as correlation functions already decayed to zero before the noise sets in. Okay. So that's an idea that's being used quite often to sort of make sense of say quantum of quantum data and quantum devices nowadays. Okay, so one very natural question is what kinds of things do extrapolate correctly, and there are two limiting cases that obviously should work. One of them, which one can check explicitly, there's for example a paper we wrote last year, is that correlation functions in systems with no conservation laws are going to decay exponentially no matter what, and they've decayed exponentially before the noise kicks in. So noise does nothing except like give you a tiny change in the decay rate. So that works okay. It extrapolates smoothly. On the other hand, if you think about something like a diffusion constant, your intuition should be as long as the noise conserves, say, the charge that's diffusing, adding the noise should do very little. And so you might expect that you'd get the same asymptotic behavior with and without noise, except that, again, the diffusion constant is very slightly modified in the presence of noise by a factor that depends on noise strength. So again, it should extrapolate nicely. And so, these are the two extreme limits of that, the system, in a system with, say, one conservation law, you might say that everything either behaves hydrodynamically or like it doesn't see the conservation law at all. That might be some intuition. But in fact, we find that there's an intermediate type of object, which is the simplest example is single particle Green's function in a system with charge conservation, and this thing does not extrapolate correctly. In fact, this thing is extremely sensitive to whether your underlying problem is quantum coherent or not. And so I'm going to explain why that's the case in the rest of this talk. Okay, so fine. Any questions so far? All right, I'll keep going. I'm still audible, right?
Yes, yes.
Okay, terrific. Fine. Okay, great. Okay, so what I'm going to think about is I'm going to think about a system with a conserved U1 charge, which is the sum over particles numbers in all sites. Or I can think about it as in many of the spin chains we like to think about the sum over sigma z on every site. And I'm going to say this thing is going to commute with my time evolution operator, which is unitary. Yeah, so I'm going to think primarily about the unitary case, and I'm going to discuss what noise does. So the important thing is that the evolution operator, as long as I do have this conservation law, is block diagonal in this object Q, in the sense that when I think about the Heisenberg evolution of an operator, it's only, and let's say that the operator is, for example, the charge. The charge has the same number of creation and annihilation operators in it. So sigma z, for example, I can write a sigma plus, sigma minus. So it's got the same number of sigma pluses and sigma minuses in it. And when I time evolve it, it's going to keep having this property. It could go from sigma zi to sigma zi, sigma zj, which has more sigma z's, but it's still got the same number. Still got two sigma pluses, two sigma minuses. It's got the same number of creation annihilation operators, and that's implied. That's a consequence of this U1 symmetry. And so I can classify my operators based on the imbalance between the number of sigma pluses and sigma minuses that show up in the operator, and this imbalance is a intrinsic property of the operator that survives under time evolution. So if I take sigma plus and I time evolve it, it's going to keep turning into things that, for example, it can turn into sigma plus, sigma plus, sigma minus, but it can't turn into sigma plus, sigma minus. So in particular, it cannot mix with the charge or the energy or any other hydrodynamic mode under time evolution. And so that means that I can classify my operators based on this the pseudo charge, the Heisenberg picture charge. They're written as fancy Q, and the Heisenberg evolution leaves this property alone. And so all the hydrodynamic operators belong to the sector where fancy Q equals 0. And now I'm going to talk about operators that don't live on in this diagonal block. They live off the diagonal block. It doesn't matter if my purpose is how far off the diagonal block they live. So I'll focus mostly on the case of operators that live like one step away from the diagonal block. The question I'm going to ask is why would operators like this feel hydrodynamics at all? Very naively, you might say they shouldn't. And the reason they shouldn't is if I pull up this picture of slow and fast, if I pull out this picture of objects in the path integral that survive dephasing, these objects consist of equal numbers of particles on the Bra and the Ket side of the time evolution, and that's where their parallel decay in time comes from. And that's true of everything in mixes with the hydrodynamic operators as well. They, so if I apply, for example, the density operator, I'm going to move some of these guys around, but I'm going to leave this property alone that I have the same number of particles in the Bra as the Ket side. On the other hand, when I'm constructing something like a single particle Green's function, what I'm doing is I'm looking at an overlap between trajectories that have different numbers of particles in the Bra and the Ket side, because I'm explicitly inserting in the fermion representation, I'm explicitly inserting a particle, time evolving, and then taking it out. So the two sides of my contour, the two sides of my evolution have different numbers of particles in them. And so there are no classical trajectories that exist at all. This extra guy has no one to line up with. And so the naive picture is that it's just going to dephase exponentially. And so the surprise, if you will, is that this is not true, at least in one dimension. Okay. So why is this not true? This has to do with the physics of rare regions. To walk you through the picture really fast, let's think about an equilibrium correlation function. I can think about my infinite temperature, other finite temperature state as broken up. It's an ensemble it's a sum over an ensemble of classical configurations, and I can break up my configuration space into two types. There's the guys that have a big hole, a big void near the origin, and there's the guys that don't. The configurations that have a void near the origin are exponentially rare, but as we'll see, they're not rare enough not to be important. So I'm gonna think about the contributions correlation function that comes from taking a state that happens to have a void that is a region with nothing in it around the origin, inserting my extra particle there, propagating it for a while, and then removing it. And I'm going to think about primarily the case where the void doesn't fill in by the time t that I remove the operator. And so this piece, this is going to give me some contribution to your correlation function, and I'm going to assert that this piece is the dominant one, there could be another piece, but I'd expect, for the reason that I gave previously, that the other piece is subleading. In some cases, we can show that rigorously. In some cases, we can't, but we have evidence for it in general. Okay. So, the key point is that since we have a lot of freedom in choosing exactly how big the void is, we can't have a general cancellation between the term due to the void and the term that's due to other stuff that's not in the void. And since there can't be a general purpose cancellation, you'd expect that this contribution lower bounds the correlation function in general. Okay, so so what I now need to think about is what happens when I take a generic operator and I insert it into a void. How does it evolve? And the key assumption that I have to make, which I've got to check obviously on a system by system basis, but it's very generally true by the third law of thermodynamics, is that inside a void, the entropy density is 0. And so if I try to insert a particle into a void, it can't, if I insert a particle into the void, it can't sort of decay into a shower of other particles. All they can really do is propagate around essentially a single particle. Whenever it collides, whenever the particle I introduced into the void collides with any other particle, then I'm going to make a pessimistic assumption and say that it just dephases and is gone forever. And so what I need to do is I need to think about what the probability is that I inserted my particle into the void and it never collided with anything else. So nothing else in the system collided with it until such time as I removed the particle in order to measure the correlation function. Okay, so that's the thing that I need to estimate. And so let me walk you through how I can estimate that. Yeah, so just to say this a little more formally, this problem of asking how long an operator survives inside the void can be phrased as a non-Hermitian time evolution problem, asking, there's a decay rate, that's the non-Hermitian part that tells me if I saw another particle, and if I saw another particle, then I decay. I need to ask what's the survival probability under this non-Hermitian evolution. Okay, so I need to deal with two cases. The first one, which I have a lot of control over, because there's random circuit averaging techniques that will let me say something about it, is to talk about systems where I have no spatial or time translation invariance. So my time evolution operator is fixed and unitary, but it's just kind of fluctuating in some particular way. It's time dependent in an arbitrary way. So this would be the case, for example, in a single realization of a random charge conserving circuit. So in this case, elementary excitations are diffusive even inside a void. The diffusion constant is just set by single particle physics, and it's just some number which does not depend strongly on the density. And so now I need to say, okay, I put the particle, I created the void, time t equals 0, this profile, this density of other particles was more or less empty over here. And I put my test particle in at the center of the void. I need to ask, how long did it survive without colliding with anything else? Because any collision is going to cause my single particle Green's function to dephase. And the key point is that it survives until the void fills in. The void fills in on a time scale that's L squared if the initial void was of size L. Okay, and now we're all set to do this region counting argument. So if I want to talk about the correlation function at some time t. So what kind of void do I need? I need the smallest void, because that's the likeliest void that's going to survive until time t. And so that is a void that's got size that scales the square root of time. And the probability of this void is just exponential in its size, which is exponential in negative square root of time. And so this immediately gives you the conclusion that actually the decay of the local correlation function of this particular spectral function just goes as e to the minus square root of time. This is again not what the naive argument I gave you earlier would have led you to expect. You'd have expected e to the minus t, but instead it's e to the minus square root of time. And this is in fact very clearly seen in numerics, and it was seen in the random circuit numerics before we even thought of trying to explain it. And so this is the story in the situation with where the time evolution is random, like a random circuit. Okay, so that's one of the key points. So maybe I'll stop at this point to see if there are any questions yet.
Yeah, so why the void close diffusively? In a sense, it's a void, right? So in the void, you should be ballistic.
Yeah, I'm coming there. So I'm talking about a random circuit right now. And in a random circuit, the time evolution operator is not time or space translation invariance. Your intuition theorem is wrong.
Right.
Make sense?
Yeah, right.
Yeah, but I'm actually getting there in the next slide. Other questions?
Yes, can you please explain this this exponential, this probability P of L? You assume that P of L is the exponential of minus L.
Yeah.
Where it comes
That's
from?
right. That comes from just the fact that my equilibrium state is at high temperature, right? So when I think about so going back a little bit, so I'm looking at an object like this, so I can break rho up into sort of rho as a can be broken up as a sum over all possible projectors onto product states, for example. That's a way of breaking up my high temperature state. And so I can classify my product states into product states that have, let's say, all 0 or all 1 in a region of size L, centered at this position X, and everything else. And the probability of associated with this projector is e to the minus L.
It's a kind
It's
of
just the probability.
Poissonian distribution. Okay.
Yeah, exactly.
Okay.
And so this is true asymptotically at any finite temperature, at any non-zero temperature. Okay, great. Anything else at this point? All right. So let me keep going. There's not actually a lot else, so we'll probably finish a few minutes early. So yeah, so let me go back to the question about translation invariant Hamiltonians. So the point is, okay, so if I want to do this for translation invariant Hamiltonians, as was pointed out, you can't really assume that the dynamics inside the void is diffusive. In fact, once a particle escapes into the void, it just propagates ballistically. And so this poses a problem because the naive argument I gave you previously is not going to work. The diffusion constant is density dependent, and it diverges as 1 over density. The reason it diverges 1 over density is because, in general, the mean free time scales as the inverse collision rate because the diffusion is due to collisions. And so in order to figure out how the void fills in, what we need to do is we need to solve this nonlinear diffusion equation with a singular density-dependent diffusion constant. It goes 1 over density. And this is something one can do. And there's both a scaling solution that you can look up in the literature, and you can also explicitly go ahead and solve this diffusion equation numerically on large scales. And what you find is that there's a pretty good solution that gives you the density of the center of the void goes as T over L squared with some correction, which I'll come back to if I have time to talk about it. So we need to basically plug this density profile into my non-Hermitian evolution operator inside the void, and then just see what the leading eigenmode of that non-Hermitian operator is. with this particular density profile plugged into it. And that's something that's a straightforward exercise, but we can also do it sort of at a very rough intuitive level. Yeah, so one comment is that in general, when I insert a particle above the void, I'm going to find that that unless I have some extra symmetries, the dispersion for my particle is going to be quadratic. And so in order to understand how this non-Hermitian evolution operator works, you Taylor expand the evolution operator for the particle I inserted into the void about zero momentum. It gives you a quadratic momentum dependence, and then it has this non-Hermitian profile. You can see that it's a harmonic oscillator with an imaginary potential. And so one important point that comes from this analysis is that the longest lived modes of this non-Hermitian Hamiltonian are quite tightly confined near the origin, like oscillator wave functions. They don't really explore the ends of the void. Okay, and so this allows you to rather quickly estimate what the decay rate should be. And the argument now goes like this. So I want to talk about the correlation function at a time t, and this correlation function is going to have contributions from voids of all size L. And the contribution from a void of some particular size L has two pieces. One of them comes from the fact that the probability of the void is exponential in its size. That's e to the minus CL. But it also has the fact that the bigger the void is, the longer the correlation function has lived inside it, and that's the second factor. The decay rate comes primarily just from the density of particles that have made it to the center of the void, and that scales as T over L squared, and that sets the decay rate. And so that gives you this particular equation, and so now this is summed over all sizes L. You can take the saddle point of this equation, and the saddle point solution is when L goes as T to the 2/3. And so this immediately gives you the prediction that correlation functions in this generic Q1 situation decay at e to the minus T to the 2/3. And this prediction is something that we can then go and check, and we checked it in a variety of models, and of course this is much harder to do than the random circuit because you're reliant on matrix product simulations of chaotic quantum systems. They're not particularly reliable at late times, but in all the models we looked at, in fact, you do see a very nice collapse to this stretched exponential decay of the correlation function. So it seems like these voids really are doing the thing that we think they're doing. All right. So one very important point to make about this result is that it really depended on the assumption that the void had zero entropy. And this assumption makes complete sense if you're talking about a system that has Hamiltonian or unitary evolution because nothing's sitting inside the void. But now the key point to remember, though, is that even though I've been thinking about the decay of the correlation function, actually the correlation function in a given run of the evolution, for example, for a particular Hamiltonian, also has a piece in general that's going to be picking up phase. It's going to decay in the stretched exponential way, but it's also going to maybe have some random phase that's attached to it. And this phase is going to be rapidly oscillating in time because there's no reason for it not to be. Okay, and in order for this thing to survive in an ensemble of systems, you need to say, okay, how big was the correlation function? Let me compute the correlation function, compute the size of it, and then average that over systems. So this way of doing the averaging is going to preserve the coherence. You can think about it as just actually being able to do an individual circuit, compute the correlation, find the correlation function there repeatedly, and then go and average it over circuits. But if you have noise, of course, that's not what happens. In fact, in the presence of any dephasing noise, you're going to have decay even inside voids, or dephasing even inside voids. And effectively, what the noise does is it sort of averages this random function inside, it averages with its sign. And so the basic point is that once you have noise, even though the envelope that we're talking about so far is decaying sub-exponentially, it's multiplied by an exponentially decaying signal. It just comes from averaging a bunch of oscillating functions. So in general, what you expect is once you put noise in, you will just have exponential decay of the correlation function, and there's going to be a crossover between the stretched exponential and regular exponential behavior on a time scale that's set by the noise strength. So that's the story of what happens when you put noise in. So this is, in some ways, maybe surprisingly, a simple correlation function in a very generic many-body system with essentially no structure except unitarity and U1 conservation, but it seems extremely sensitive in its asymptotics to whether the system has noise in it or not. And that's really the punchline of this talk. Let me just say, I don't really have time to discuss this in any depth, but if I wanted to do this calculation in the random circuit ensemble, what I can do is I can compute this particular moment over the correlation functions, and I can write this, as some kind of transition amplitude for 2 copies of the density matrix. And if you don't know how this game is played, don't worry about it. But let me just say that in this case, you can convert what I said above to an explicit lower bound for the survival probability in the correlation function at all times. And the way you do that is by sort of writing down the stat mech model and then constructing a variational approximation to a variational bound to the correlation function using a variational state that's derived from this void picture. Okay, so that's most of what I wanted to say today. So the summary is that rather surprisingly, you have signatures of quantum coherence and the decay of quite simple correlation functions. Things don't just behave like the couple to Bath. The way I like to say this is that a many-body system, yes, it acts as its own Bath, but the Bath has holes in it. And so the holes are precisely these voids, and inside these holes, the Bath is not effective at dephasing correlation functions. And so at least in one dimension, there's still enough of these holes in the system. They last for long enough. They can dominate the decay of these simple correlation functions. It's not clear to what extent this stuff survives in 2D. That's something we're thinking a bit about. But even more generally, you might ask, if this, what are the, so you could ask, does it affect, for example, even if it's not dominant in the decay of correlation functions, can it affect things like the pole structure of the single particle Green's function in higher dimensions? And that's something that it might do, even if it's subleading effect in the correlation function. Okay, so many open questions here, but the main result was what I said. I also, I guess I don't have any time at all to talk about this, but I also wanted to advertise this other result that's related in the spirit of having to do with the zero noise limit, which is that we've been able to construct chaotic systems in which the diffusion constant is a discontinuous function of noise. So at any finite noise, the diffusion constant converges to some value, but the zero noise limit is totally different. It's a totally different value. We had an example for this in integrable systems with Jacopo and Rama Vassar and others a few years ago, but now we have one that just happens in totally chaotic systems. You can ask me about that in questions. Okay, let me stop here and take questions.
Okay, thank you, Sarang, for this very nice talk. We have plenty of time for questions, so we actually have 10 minutes. So questions for Sarang.
Okay. Does it require that you are on a lattice? I mean, at which point it is important that you're on a lattice? And more specifically, what happened in the limit x and y the same? Like, this is following up a discussion we were having on the stage, because, like, for example, if you think on the lattice, like, side x by x, that would be like just the density, then it would be hydrodynamic again. So I don't know. Maybe
that's right. Yeah. So I mean, I'm thinking about U1 on the lattice because I want particles to not move ballistically, right? So if I'm in the continuum, then I think there's nothing to stop my void from just filling in ballistically. So on the lattice, at least typical regions are diffusive because of umklapp scattering, if you like. So it's hard for the, even so when you have the void and you have translation invariance, it's just hard for things to get inside the void. I mean, once they're inside the void, they can move really fast. But there's sort of traffic jam at the edge of the void, and that's set by the typical diffusion constant. So that happens on the lattice, and I really don't want to think about the case where, for example, I have the Heisenberg model because they're like this object that I'm talking about is hydrodynamic again, like you say. So in that case, I have another conservation law in the sector, and so the stuff that I'm talking about, I mean, the stuff that I'm talking about is still at some level true, but it's subleading to the physics, the hydrodynamics of the filling in of, so the correlation function already has a long time tail. So stretched exponential is kind of irrelevant because its leading behavior is just a power law. So I want to, in order to see the stretched exponential, I need to look at things where it's not sort of hiding underneath a power law, basically. That's why I'm sort of focusing on a case where I can sort of pull it out from all the power laws by going to the right sector of operator. That makes sense?
But by the way, I mean, shouldn't you see this stretch exponential also in the entanglement then, in the same way that?
Yeah. Well, the stretched exponential shows up as a power law in the entanglement, and so one of the sort of side results of this paper is that there's this belief that the Renyi entropies go as t to the 1/2 in a diffusive system. In fact, that's not the case for say Hamiltonian. They should go as t to the 2/3.
Has been checked numerically?
Yeah, I mean, again, not very convincingly, but if you go back to the old 1/2 results, like the only thing that you can really convince yourself of is they're not one, right? There's some, yeah, these things are quite difficult to get good data on, but it's the data is all consistent with 2/3 as well. But yeah, that's something that's interesting to check in future work.
Okay, other questions?
Even the stretch exponential decay comes in even in classical lattice gas models where you have large number of conserved quantities, but I don't think they are under the GHD. Do you see any kind of relations with those?
I think those are just different. I mean, there are indeed some different mechanisms to stretched exponentials. In classical lattice gases, yes, the point is that, yes, I guess one has to go look at that case to see if there's any similarity in the mechanism. But the object I'm talking about, which is, this sigma plus sigma minus correlator, isn't even like a legitimate correlation function in a classical lattice gas, right? Because there's no notion of the bra and the ket disagreeing. So I'd need to be talking about something like an overlap between two copies of the evolution in that case to even define this object. So I'm not completely sure how one would map from one case to the other. Because yeah, the sort of the notion of an off-diagonal operator, a single particle Green's function of this type, I think it's sort of I can think about finding versions of it in classical Hamiltonian systems, continuous state spaces, but I thought a little bit about automata and lattice gases, and I just don't think that these objects exist there. So it's not completely clear how one would do the mapping. But yeah, indeed, there are situations, like quite simple situations, like if you had a diffusion constant that vanished at some point inside the lattice gas, For example, if the diffusion constant vanished at low density in a facilitated model or something like that, then you can make a very similar void-like argument to give you a stretched exponential for, say, something like, the finite momentum conductivity. So similar void-like mechanisms do play a role in classical physics, but the specific object I'm talking about, the single particle Green's function, I don't think is even defined in those settings.
No, this is the case of stochastic lattice gas with deposition evaporations. And you can show that the Markov matrix also gets sectorized in different blocks, and you can generate different exponents. It's one of the early works of Deepak. I don't know if he's present here.
Right. So what determines what indexes the blocks?
They have a nice way of constructing strings of conserved quantities by reducing some things, and so they call it, I think, infinite strings of, I forgot the name. They have a unique way of defining the conserved quantities in the lattice gas model.
Yeah, no, I'd be very interested to look into that further. I mean, obviously, it's very different in many ways from what I'm talking about, because here there's not a pair of conserved quantities, but indeed there might be some similarities. I mean, in some sense, most stretched exponentials come from this mechanism where you have like a family of exponentials summing over them. But yeah, it'd be interesting to know what this has to do with that. Thanks.
Thank you.
Okay, any final question? Not the case. Let's thank Sarang again.
Thank you very much.